What I want to look at here is the photoelectric effect. Again, reasonably basic stuff, but we're just trying to get up to speed. We want to get a few things out of here. So let's just start with a little drawing of a basic setup for doing something with this. This little bit of metal in here would become the emitter of electrons, and we'd shine a light on it. So this would be a light. And this whole setup would be put in a circuit with an ammeter there and a voltmeter here. So you might see the circuit in some questions. And what you expect to happen is that when a light shines, and we keep this at a set frequencies, that the light contains energy, the photons contain energy according to E equals hf. Now, it was Einstein that basically came up with a description of what was happening here, and he basically was the one that said, well, Planck had said that these little oscillators could have discrete units of energy, and then maybe photons could act like that. I don't know that he actually believed it. He was just sort of proposing that, hey, maybe it works like that. I don't think Planck at that stage believed it. But this is what they came up with. This was one of the major things, though. I think in 1905 there were three great ideas from Einstein. One was the relativity, one was this photoelectric effect, and one was a proof of sort of the atomic nature of matter, or when I say atomic, I mean the fact that atoms exist. He proved it mathematically. Anyway, so the light shines, we get some electrons emitted. If these electrons have enough energy, they're going to reach across here. This whole thing's obviously in a vacuum, and we're going to get a current. So the voltage here, you're going to apply in a way, we've got the negative on this side to repel the electrons and stop any current from flowing. So the level of voltage you have to apply will be a determining factor in how much kinetic energy those electrons must have. Now, the electrons first have to be released from the plate, and what they found with this whole photoelectric thing was that depending on the metal here, so this metal here was very specific, that you didn't necessarily get any electrons released no matter how intense the light was. And then if you change the frequency of the light source as your frequency went up, even if your frequency even if your intensity was very low, you'd then start to get a current. And that was interesting because it didn't seem to depend on intensity, it seemed to depend on frequency. And this led the whole thing towards the fact that the light comes in these discrete packets which have that much energy. Even if there's just one of them, it has that energy. So we're getting away from this whole continuous idea that you've got this continuous spectrum of, excuse the sort of pun, which energy can sort of operate over. And so you had this whole wave description of, well, obviously if wave is just, if you increase the intensity, it wouldn't really matter what the frequency was, you just get more and more, and that would give the energy to the electrons and they'd be freed up. It didn't work that way. So we now see it that if you've got this low frequency, no matter how many of them you've got, they're all too low in energy to give the little electrons here enough energy to escape the plate. The energy required to escape the plate is what's called our work function. So when you get the right frequency, you got enough energy for the electron to escape. Now, if you give it more energy than that, it not only escapes, it's got kinetic energy, and it can move. Now, the amount of kinetic energy it's got will be equal to the voltage required to stop it. It's sort of like when we throw something up in the air, the EK, or the kinetic energy, okay, then gets equal to the potential energy. So the potential energy required to stop this thing moving forever, or the EK, must be equal, right? So the energy that we apply with the voltage is like putting a potential energy there, so that the kinetic energy these little guys are released with, there'll be a set height, if you like, or a set potential energy at which all that kinetic energy has been used up. And so if you set the voltage, you can stop the current. the voltage being equivalent to the potential energy you created, equal to the kinetic energy they gained because they were given too much energy by the photon. So all this means that we can have this formula which says HF for the photon that you've sent down there will be equal to the work function. If it's just equal to the work function, they'll be released. You won't need any voltage to stop a current. But if they've got more, then they're going to get some kinetic energy, and that must be equal to the voltage, the reverse voltage, if you like, to stop them. So we can write that down. The energy, or the energy of a voltage, as you know, is just VQ. All right, voltage times the charge taken through that voltage is the energy. So now we've got our equation. If we solve this equation for V, we can say V equals HF minus work function all over Q. And that we can graph. Hopefully everything's still there. And we get graphs like this. And you can see the graphs are always going to be, this is, by the way, voltage against frequency. The graphs are always going to be these parallel lines for these different types of metal. And these different types of metal have different frequencies at which the energy will equal the work function. So this is the threshold frequency. So this metal requires a greater frequency, therefore it requires greater energy just to release the electron. Alright, so the height above here then becomes a measure of the kinetic energy they gained. So what are the intercepts on this graph? The intercepts are work function over Q, and that's a negative number. Although the work function itself obviously was positive energy. We don't have negative energy. Well, maybe we do, but it's another discussion. So work function over Q, that's a measure then of the work function. Again, bigger the frequency, bigger the energy required to release it from the metal. What's the gradient on this? The gradient is H over Q, so we just have to multiply by Q to get H. So the gradient equals H over Q. So doing this simple experiment, which we could do, we can determine Planck's constant, the most important constant just about in the whole universe. So this was a pretty cool experiment. What else can we see from this? Well, this is a voltage measurement because this whole axis is voltage. So work function over Q equals volts, right? So if we want to turn that back into joules, because V equals energy over Q, then if we've got volts, we multiply that by charge. Then we've got the work function in joules. So we multiply by that one over Q times Q equals the work function in joules. Right, and if we then divide by Q, we convert it back into electron volts. So what we find with that is that although this voltage reading over here is a voltage reading, if it's down here at minus 2.2, then just from that little calculation we've done, that's the work function for that metal in electron volts. So typical numbers are sodium equals 2.28 electron volts. These are work functions. Iron equals 4.5 electron volts. Let's see, copper equals 4.7 electron volts. So you get an idea. Sodium has a very, very low work function, doesn't require much energy to release it from the metal compared to copper. Any with really high ones? What's that one that I've got there on my list? Lead? No. Don't know what that one is. They're around about 4s mainly, except for that sodium. Alright, so that's photoelectric effect. Sorry about the sunlight. It's